This is General Chemistry. Cover the topic of gas, part 1. For gas, we'll be looking at two parts, microscopic and macroscopic. For the microscopic part, we'll be looking at gas as tiny particles. But for the macroscopic part, we will consider gas as larger entity. For example, gas in a container or gas in a balloon. For the microscopic part, we'll be using kinetic molecular theory or KMT to help understanding it. But for the macroscopic part, we'll be using gas law, which will involve pressure, volume, and temperature. Let's take a look first at the microscopic part of the gas. So, what is kinetic molecular theory or KMT? KMT is pretty much a model, and model is pretty much an approximation. And even though kinetic molecular theory is simply an approximation, it still can help us understand how gas behaves. So let's take a look first at these approximations. First, gas consists of very tiny particles. They can be molecules, they can be atoms. The rectangular box here represents a gas container, and the red circles here represent gas molecules or atoms. If these red circles are helium, neon, or argon, they will be considered gas atoms or monoatomic molecules. But if they are oxygen, nitrogen gas, or ozone, these are polyatomic molecules of gas. And these gas molecules are so tiny that their individual size or volume is negligible, which means that these red circles up here, their volume is simply zero. And these gas molecules tend to move in straight lines in random directions. And if they move and collide with the container wall, that will contribute to pressure. What I mean is this. These molecules or red circles can move in many random directions. But when they hit the wall, that part will contribute to pressure. So now we're starting to see relationship between the gas molecule, which is the microscopic part of the gas, and the pressure, which is the macroscopic part of the gas. And the next approximation is that these gas molecules neither attract nor repel each other, which means there's no intermolecular forces, no dipole-dipole, no hydrogen bonding in this KMT model. And nonetheless, this gas molecule can still collide with each other, and this collision is considered elastic, which means there's no kinetic energy loss in this collision. And this average kinetic energy of the gas molecules tend to be directly proportional to temperature in Kelvin, which means if temperature goes up, the kinetic energy will goes up too. And if temperature goes down, the kinetic energy will goes down too. You may remember that kinetic energy tend to be equal to half of the mv square, and v here is speed or velocity, and in this case is the speed of the gas molecules, and we will actually be looking at this in the next topic in this video. In this topic, we will be looking at Graham's law, and the key concept is that heavier gas molecules are slower than lighter gas molecules. This seems pretty straightforward. However, you may see this Graham's law hidden in different circumstances. For example, in effusions or in diffusions. So let's take a look first at effusions. Here we have a container of gas molecules, and on the surface of this container, there is a tiny hole in here. And when there is a tiny hole, gas leaks. And heavier gas molecules tend to leak or effuse more slowly than the lighter gas molecules. And in some cases, they may give you a balloon. And in this balloon, there are gases such as helium, or sometimes nitrogen, oxygen, carbon dioxide, or the mixture of these gases. And on the surface of this balloon, there are pores. And when there are pores, gas leaks. And heavier gas molecules tend to leak or effuse more slowly than lighter gas molecules. So that is effusion. How about diffusion? In this case, we have a container with a divider in the middle. Left part of the container contains gas molecules and the right part is empty. And when that divider is removed, gas will diffuse from the left part, which is more concentrated, to the right part, which is less concentrated. And the heavier gas molecules tend to diffuse more slowly than the lighter gas molecules. So if you come across effusions or diffusions, you can relate it back to Graham's law. They all use the same concept. And in some cases, we can even calculate or approximate the speed of the gas molecules. We are given two formulas here. V, which is speed or velocity of gas molecule, can be equal to square root of 3 kT over small m, or square root of 3 RT over big M. V is an average speed of the gas molecule, or root mean square speed, and in some cases, they may call it VRMS. K here is Boltzmann constant, and little m here is the mass of the single molecule, and R here is the gas constant, and the big M here is the molecular weight of the gas in kilogram per mole, and T is the temperature in Kelvin. So if you are given little m, which is the gas of single molecule in kilogram, you may use this formula. But if you are given the value of the molecular weight or the molecular mass of the gas, and it needs to be in kilogram per mole, then you can use this second formula. And normally the Boltzmann constant K and the gas constant R are usually given in the exams, so you should not need to memorize that. So let's take a look at how we can use these two formulas to calculate the average speed of the gas molecules. In this question here, they ask us to calculate the average speed of nitrogen gas molecule, or VRMS, at 27 degrees Celsius. So we're gonna try using both formula. First, it is V equal to square root of 3 kT over small m. And another one is V equal to square root of 3 RT over big M. So let's try that. For this one, we have 3 here, and K is 1.38 times 10 to the negative 23 joule per Kelvin, and the temperature is 300 Kelvin, and then it divided by 28 AMU, which is the mass of single molecule of nitrogen, and the conversion of AMU and kilogram is 1.66 times 10 to the minus 27 kilogram per 1 AMU, and that's still in the same square root here. Alright, so you should be able to get 516.9 meter per second here. And how about the second formula? Here we can try plug in 3 and the R gonna be 8.31 joule per mole Kelvin, and the temperature is 300 Kelvin. And the big M, which is molecular weight or molecular mass of nitrogen gas, it is normally given in 28 gram per mole. So we have to convert it into kilogram per mole, which should be 0.028 kilogram per mole. And you should be able to get 516.8 meter per second. And these two answers are approximately the same. They are really similar, which means both formula work and you can use them in your exams.